I think we can start. Third lecture, right? Okay, please.
So let's recap briefly where we are. So we started with some algebraic variety. And from this we build a stable infinity category of quasi-coherent sheaves. Max. And so, sort of the main theme is to sort of study this correspondence, how things on one side reflect structures on the other side, and vice versa. So the first, so we've already seen a few properties of this assignment. It's functorial in a certain sense. So if I have a map, I get two functors. So there's a push-forward functor. And quasi-coherent sheaves on x, and quasi-coherent sheaves on y. And there's a pullback functor going in the other direction. So one thing I didn't mention before that I probably should have is that the push-forward functor is the rate of geometry of the pullback functor. But never mind that. So these satisfy some properties. So this is functorial, so both of these are compatible with composition. Furthermore, we have what's called flat base change. So if we have x mapping to y and y prime mapping to y, so we can consider the fiber product. Let's give these names. Maybe f prime, g prime. Yeah, that's good. So if it's so if we have a fiber square and say f is flat, then there's an isomorphism. So between, we can start here, and first you pull back with respect to g, and push forward with respect to f prime. Or we can first push forward with respect to f, and pull back with respect to g prime. And these are isomorphic. So this isomorphism of functors is only true if f is flat. So otherwise, in general, there's a morphism in one direction, which is not an isomorphism. The desire to eliminate this requirement is one of the motivations for enlarging the category varieties to considering derived things. So probably we'll see more of that in some later talks. So just throw that out there, that this is one motivation, is to make the base change formula always true without any hypotheses. So that's an important fact. Let's call this 1. Let's call this 2. So the third thing, which came up implicitly, is that this category is a tensor category. So I didn't define the tensor product explicitly, or really even say what it means for an infinity category to be a tensor category, but you can probably imagine, or at least roughly. And the tensor product is the one, well, it's the one that's on affines is just tensor product of modulus, or complexes of modulus, so the derived tensor product. And sort of formally, this extends to all varieties. That's one of the advantages, by the way, of this definition and defining it in terms of an inverse limit over affines, is that any structure that you have on affines, if it's sufficiently natural, it automatically generalizes to an arbitrary to an arbitrary variety, not necessarily affine. And what I wanted to say about that, so there's also a compatibility between these functors and the tensor structure, which is very important, which is called the projection formula. So it says the following, that again, if I have a map from X to Y, and F tensor G is isomorphic to F star of F tensor F upper star of G. So F here is a sheaf on X, and G is a sheaf on Y. So anyway, this is one of those basic compatibilities. And again, the way you prove this kind of thing is essentially by checking it that it's true for modules. It's pretty clear, I think, for modules that this is the case. So now, so those are kind of the basic features of this association. So now, at the very end of last time, we computed the derived category of P1, and the way we did that was by describing the identity functor as a kind of integral kernel. So we can consider more general integral kernels. So if I have X and Y and the sheaf on the product X cross Y, this gives me a functor E sub F from quasi-concurrent sheaves on X and quasi-concurrent sheaves on Y. So the first projection map and the second projection map. So it sends a sheaf F. Well, sends a sheaf F to well, you first pull it back, tensor it with F, and then push forward with respect to the other projection. So that's as we saw, at least in the case of the identity functor, this was a very profitable viewpoint on functors. And in fact, more generally, it's an extremely useful viewpoint for lots of reasons. Hopefully we'll see some of them. But so the thing that I wanted to...
is there a characterization of functors that can be written that way?
Yeah, I'm getting to that. So first I want to state an exercise, which is the following. Suppose I have F and G that I can take E sub F. I'm sorry, so F is in sheaves on X cross Y. And G is a sheaf on Y cross Z. So I can take a composition of the corresponding functors. This gives a functor from sheaves on X to sheaves on Z. So the exercise is that this itself is given by an integral kernel. Let me call it maybe H. So where H is the following guy. Let me call it. I'll define what these letters mean in a second. Star of upper star F, tensor pi, upper star G. So let me tell you what these maps are. So we have x cross y cross z, and this projects onto, say, xy, x cross y, and this is pi xy. Similarly for the other projections. So this is the exercise. So let me give you a hint as to how this might be done. So the hint is to use base change. And the projection formula. So namely, well, let's start with the base change part. So suppose F and G were just structure sheaves. We're just O on the products. Well, then what you would say is that you have two correspondences like this. So you pull back here, you push forward here, you pull back here, you push forward here. This is what you're trying to express. But now, pushing forward here and pulling back here is the same as if we take a fiber product and pulling back here and pushing forward here. And both of these maps are flat, so there's no problem with the base change formula. And the point is the fiber product here is x cross y cross z. So it just amounts to just pulling back to x cross y cross z and projecting down. And in order to incorporate f and g into this is where the projection formula comes in. So, well, I'll leave the rest as an exercise. I think it's a very useful exercise to do to learn to work with these things. All right. So now, at least the upshot is that this operation defines a different tensor product. And she's on the product. I'm sorry. Cross X. If I have the same thing, then I get this so-called convolution tensor product, and it's not. Well, one way you know that it's different is that composition of functors doesn't commute. You have a functor from sheaves on X to sheaves on X, and you compose two functors. Depending on the order in which you compose them, you might get a different answer. So this is not symmetric monomial, but regardless, also have a functor. So quasi-coherent sheaves on X cross Y into functors from quasi-coherent sheaves on X, quasi-coherent sheaves on Y. And the theorem, so I don't quite know who to attribute this theorem to. Probably the thing that I'm tempted to write is tau n. Is that the right attribution?
So,
okay.
right.
Is that there's an equivalence. So this is not an equivalence of categories. You have to, but it turns out that this is a full subcategory of these functors, and we can identify exactly what there's an equivalence between quasi-coherent sheaves on the product and what I'll call fun superscript L between quasi-coherent sheaves on X and quasi-coherent sheaves on Y. So what is this fun L? It's just colimit. It's just those functors which preserve colimits. So it's like an infinitary version of an exact functor. So if you reach L functors which preserve colimits. So if you're not happy with the notion of a functor preserving colimits, well, just think it's like an exact functor. Or if you're not happy with that, just think morally that this is an equivalence. That all the functors somehow the moral is of the functors between these categories, you should only consider ones which are colimit preserving. That's the kind of good class of functors, and all of those are given by integral kernels. So, I mean, already this gives something interesting. So, you know, this category, one of the consequences of this theorem is that if we know the category of quasi-coherent sheaves on X and the category of quasi-coherent sheaves on Y, then we don't need to know anything else about X and Y to identify the category of quasi-coherent sheaves on their Y. So, that's sort of a nice statement relating the algebra and the geometry of the situation. Alrighty, let's see. So next, I don't know a good way to do this without introducing this notion. So if it seems too abstract, I apologize. I'll also tell you explicitly what it is in the example, but so definition, an object of, let's say, is called compact. So, for many purposes, it's convenient not to consider all quasi-coherent sheaves, but just sheaves which are like coherent, or impose some kind of finiteness conditions. Something like, you often don't want to consider all vector spaces, but vector spaces which are finite dimensional. So in this kind of categorical setting, there's a notion called a compact object. An object F, so the definition is a little funny, but so if we map out of it into some direct limit of things, then this is the direct limit of maps. Fine. So let me try to unravel this in a few cases. This doesn't seem so strange. So for instance, suppose our category was just vector spaces, the ordinary category of vector spaces, nothing derived. What this would mean, this property exactly characterizes finite dimensional vector spaces. Let me try something like this. Maybe this is a little better. So, if you have a map from a vector space to an infinite direct sum of other vector spaces, so in general, so what would it mean what would it mean for these to be equal? For these to be equal, what it would mean is that every map factors through some finite sum. Because, it's just the direct sum of pieces into finite ones. Yeah, that's right. Because we're taking direct sum here, only finitely many of these can be non-zero. So this is exactly the property that that says that a vector space is finite dimensional if for any map from it to another vector space, it factors through a finite dimensional subspace. So this is some categorical generalization of this, but in the case of quasi-coherent sheaves, you can also identify explicitly what compact objects are. So the subcategory of compact objects X is called perf of X, which is the category of perfect complexes. And it's those so a complex is perfect. Well, roughly the idea is it's one that can be built out of by a finite procedure and bootstrapped out of a free guy. But more explicitly, it's perfect if it is quasi-isomorphic. Isomorphic to a bounded complex to a bounded complex with cohomologies well, we don't need to say that, sorry. Bounded complex of finitely generated phenomena.
So it's a dualizable object.
Oh, it's also dualizable, yeah. So those notions don't always coincide. So I gave a different notion, which is compact. Compact is not the same as dualizable. In this case, it is. But, well, one advantage of compact, unlike dualizable, is that it makes no reference to the tensor structure.
Can I ask you, because it seems that you're going to raise the first order.
Yes.
On the first order, the last line,
Yep.
this category of quasi-coherent sheaves on the product is, there's an action of quasi-coherent sheaves on X cross X on one side of the tensor category, and there's another action on quasi-coherent sheaves on Y cross Y. So these both sides
from
are bimodules over that guy and Y cross Y. Is this an equivariant map?
Yes, it is.
So I can really think of these guys as sort of like some sort of higher version of a product of two modules being the same thing as the homomorphisms of the dual of one into the other.
Exactly. So there's a notion of dual, which I was not going to talk, which I'm not going to talk about for lack of time. But see, this is like maps. What you would expect is that there should be a dual somewhere here. So there's also a notion of tensor product of these kinds of categories. But I don't want to say what it is, but I'll just tell you the answer, which is that quasi-coherent sheaves on the product is the tensor product of the quasi-coherent sheaves. But you'd expect there to be some dual. Well, one feature of these categories is that they're canonically self-dual. And so you really are taking the tensor product of sheaves on X and the dual of sheaves on Y, saying that that's counter. So it exactly fits into that kind of idea that you're describing. All right. So that's so now we have the notion of perfect complexes. So for many things, these are the ones that you really care about. But the reason to consider more general quasi-coherent sheaves is that, well, all the functors you might want are not generally defined on perfect complexes. For instance, unless your morphism is proper, then being perfect is not preserved under taking push forward. Go back is always okay. So, which brings me to another point. So So there's a homological criterion for smoothness. So I don't want to dwell on this point, except to emphasize the idea that you can test whether a scheme is smooth just purely from its category of quasi-coherent sheaves. So X is smooth if and only if quasi-coherent sheaves is smooth. So I have to tell you what it means for a category to be smooth. So definition. Oh, of course. Wow. It's smooth. If the thing corresponding to the identity functor inside is compact. So, well, that's the, so this is the, so the point is, well, this doesn't involve any geometry. You can build this just from quasi-coherent sheaves on X. And, so this gives a criterion for smoothness purely in terms of the category, as opposed to any kind of geometry. So already we see some reflections. So there's a similar statement for properness, although as far as I know, it's only an implication in one direction. I'm a little embarrassed to say that I don't actually know anything about the other implication, whether it's known to be false, for instance. So definition. Is proper if well, let me say it like this. There's a natural push-forward factor, which you can define in terms of hang on. If this push-forward functor preserves compact objects. there is a notion of for a category to be smooth and smooth and proper, and well, there are two ways this is important. One is because sometimes this, even if this is not, it doesn't actually imply being proper. Sometimes this is enough to get what you want. And the other reason these are very useful things is because sometimes you want to apply this to more general categories than just quasi-coherent sheets. So, for instance, from the point of view of mirror symmetry, well, mirror symmetry says that, well, the category of coherent sheets or quasi-coherent sheets is supposed to be equivalent to some version of the Fukaya category on the mirror. And so this gives a dictionary about translating properties from one side to the other, such as smoothness and properness. Okay, so this is something you can formulate about the Fukaya category, for instance, whereas there's no other definition there. All right.
Why did you take the product here?
Oh, yeah. The reason I took the product is because otherwise there's not a well-defined. That's where I could have not taken the product, but I can't define that without reference to X, this push-forward function, because I need to know the map X to. So part of this definition, part of what's implicit about this definition is that there's a canonical. Oh shoot. oh shoot, I did not want global sections here. So I wanted this functor to be from identity. That's the functor I wanted to take. So anyway, the push forward I can't define just in terms of a category, right? I need to know about all. There's no, if I just know about the category and don't know about its tensor structure, there's nothing to hum out of. Whereas in this category there is. So sorry, hum out of the identity functor. That's some version of global sections. Anyway, I hope I didn't screw that up anymore. Is that okay? Is there?
Yeah, no, I'm just trying to unravel what is home of the identity there. So you're viewing the left-hand side there as functors from classical coherence on X to classical coherence on X, and now you're taking the identity there. Okay.
Yeah, that's right. So you take the diagonal bimodule, if you like, and come out of it. And this has to preserve compact objects. All right. So
sorry. So what is the intuition? So if
So
it's restricting to the diagonal and taking global sections.
well, no. The intuition is this: that something is what you would want to say, what you can't say a priori, is that something is proper is if you start with a perfect complex and you take its cohomology, then that's finite dimensional. This is the idea of something being proper. But you can't say that because there's no version of global sections in general. There's no cohomology in general. So this is some approximation to this. This is, I think, if I'm not mistaken, this implies the at least when X is smooth, this implies finiteness of cohomology. Yeah. So, but that's the sort of thing you're trying to capture in a way intrinsic to the category. That's sort of the idea. But anyhow, I don't know. I mean, this is I haven't said anything about the field theory picture, but this is something that's very natural from that point of view. I don't think I'll get to say anything about that, unfortunately. But maybe let's not dwell on this too much. The other notion that's very important in geometry is the notion of a Calabi-Yau. So I want to talk about what a Calabi-Yau structure is, or generally about Serre functors. So it starts with Serre duality. Well, if X is a projective variety, then Serre duality says that, some version of the classical statement. So we can consider case of X, which is the canonical line bundle. This is, in this case, equal to, dimension n. So this is equal to n top form. So this is equal to the top form, so omega m. In this case, so what Serre duality says, I hope that's a familiar statement, maybe formulated in a slightly unfamiliar way. Well, is that if you take xi from f to g, that's the same as make sure to get this right, x to n minus I of g f tensor Okay. So this is what, so usually it's formulated in terms of homology of sheaves, but it's an easy reformulation. So the idea is, well, so let's define the dualizing complex, which is, in this case, would be kx to minus dimension of x. So this is called the dualizing complex.
Which is that?
What's that?
Dimensional x is n, right?
Yeah. Dualizing complex. Oh, and if we define S sub x. Oh, yikes. I forgot to say so F and G have to be perfect complexes. Otherwise, you run into problems with duals very quickly. Double duals, isomorphism. So if you define, so there's a self-equivalence between quasi-coherent sheaves, which is given by tensoring with omega. Tensor omega x. Well, this is you can sort of formulate this relation in terms of this Serre function, in terms of this function, which is called the Serre function. So let me just give an abstract definition. So C stable infinity category as Serre function. We're doing this in this generality, but is an equivalence, is a self-equivalence from C to itself, and together with, so there's some additional data in addition to isomorphisms, I'll say natural, whatever that means, between between maps from A to B and maps from B to S of A. So you're supposed to give natural equivalences like this, dual. So in the case of a projective variety, this functor, it amounts to exactly this statement. So this is some abstract characterization of what Serre duality is doing. And well, I'll just state the main result in this business is if a Serre functor exists, it's unique. Up to natural isomorphism. It's not a terribly difficult thing to prove, but you have to sort of play with these kind of things. But anyway, so the point is, there's an intrinsic characterization of Serre duality just purely in terms of the category. So, so I want to explain one kind of very pleasant consequence of this fact. So, let's see. So one pleasant consequence is the partial answer to the question of how much the derived category of sheaves knows about our original variety. What this fact is going to mean is that in some cases we can reconstruct the variety from its derived category. So, so suppose X now is a projective variety. So there's something called its, what's the name? Let's forget the name. So there's something called the pluricanonical ring. So we can do the following. Okay. So we can take the direct sum over all I h0 of x, kx, tends to I. So we can take such a thing. It's a perfectly fine ring. And, well, the point is, for formal reasons, there's a what I want to say is this. So if X is ample, let me not say what this means. Then there's an natural isomorphism from X, between X and proj of this ring. So this is a braided ring. You can consider there's a construction similar to spec, which is called proj, which takes braided rings and produces projective varieties. The idea is, well, if you have a regular ring, what is spec of it? Well, it's just you sort of consider all possible polynomials in those variables, satisfying their relations in the ring. If you have, let's say, a presentation, here here you look at only homogeneous ones and up to scale. But anyway, doesn't matter what it is. The point is that if this is ample, then X is determined by its pluricanonical ring. So now the observation or theorem maybe is we can recover this pluricanonical ring from the derived category. So this proceeds in several, really in 2 steps. One, the Serre factor which is something that is canonically associated to this category. So it defines a bimod, it defines an element of quasi-coherent sheaves on X cross X. And this defines maybe the element which is the push forward of the dualizing complex. That's the bimodule that represents this. That represents the Serre functor. So we've got this guy, and the second step is that if we have F and G in the heart, in the abelian category of quasi-coherent sheaves, then if we take H0 of maps from delta lower star F to delta lower star G, that's isomorphic to just H0 of max. From to G. So what have we done? We wanted to know about sections of K and its powers. So we recovered omega, which is the same as recovering K, as long as we know the dimension of the variety. We can shift back. And then we can take, so this defines some object, we can take tens of powers of it, and take H0 of mass. And this exactly recovers this ring. This is roughly how you do it, except I haven't told you yet how to recover the dimension. That's the only remaining thing. And so let me tell you how to do that and more. In fact, we can recover pretty much all of the cohomology of X from its derived category by looking at Hochschild cohomology. So definition is that, let's say, Hochschild cohomology of X. So I apologize for the atrocious notation in advance. By this, I mean the chain complex. And then if I put some variable into star, I'll leave that homology group. Frequently people write some CH or something like that. But that's even more, I find that to be even more confusing. So, if anybody has any suggestions.
Underline. What about underline?
Underline? Like this? Yeah, that's good. Okay. So this is defined to be delta lower star OX tensor over OX cross X and delta lower star of OX. Maybe global section for this. So that's a pretty abstract definition, but let's see what it does. So first of all, first observation. So a priori, the way it's defined, it's an invariant of X, not its derived category. But because we have this relationship between functors, and because we understand what sheaves on the diagonal are, or sheaves on the product are, and what delta lower star is, so the first fact, so I guess maybe corollary, let's see, this, of the theorem, which I attributed to Bertrand, is that this Hochschild homology is really Hochschild homology of quasi-coherent sheaves on X. In other words, this formula makes sense. You don't need to know about X to study its to get its Hochschild homology. So similarly, Hochschild homology is this is just going to be Hom in OX cross X between delta lower star OX and delta lower star OX. So by seriality, of course, these are dual. So now, in the last few remaining minutes, let me state some properties of Hochschild homology. So the basic fact is a theorem due to Hochschild plus Rozenblyum. So it's got a fancy name, but it's a very easy theorem, actually. And you can do it as an exercise, I think. It's just taking a Koszul resolution. Is that, well, let's see if I can state it correctly. So this is equal to, really hate this notation, but let's go with it. Because the lower index suggests, so that the whole time I've been using cohomological convention for chain complexes, and lower indices suggest cohomological. And I don't know whether I should stick with cohomological or switch to homological because of this index. But anyway, up to this point, it's the direct sum of, so this is in the, so this is in the homological convention. If you want cohomological, you should put a minus I here. Of H Q of X, omega Q of X. So this should look familiar. This is exactly Hodge cohomology. In particular, we've recovered the cohomology. So X we assumed was a smooth projective variety. So Hodge cohomology recovers de Rham cohomology by Hodge-de Rham degeneration. And so we've recovered the cohomology of X together with its Hodge filtration. So we went pretty far. So in particular, that's one answer to how you get the dimension. Way overkill, but that's that. So that's kind of a cool fact. So another fact about Hochschild homology.
So how do you see the Hodge filtration from the Hochschild homology?
It's just I'm sorry, we haven't quite recovered it yet, but you can. If there was a bigrading here, then.
Yeah, you need the bigrading.
But there's an extra action of GM on this, which would hurt. What's that?
You know.
Yeah. So at the very least, we've recovered cohomology, the de Rham cohomology. Anyway, the other thing that I wanted to say is that Hochschild homology is functorial. So if suppose X and Y are projective varieties, really I only need X to be projective here. And we have some integral kernel, but one which is perfect. And X cross Y. Then this gives a push, so let me call it phi sub f lower star. This induces a functor on Hochschild homologies. X. To Hochschild homology on Y. Well, there's a little bit, so, I mean, the way you get all of these things is, as always, by playing with, there's a very concrete formula, and you can apply this formula and play with some integral kernels and deduce this fact. It's not obvious, but it's not a terribly difficult exercise. But now, so in particular, as an example, take X to be point. So what we get is for a perfect complex on Y, we get a map from the Hochschild homology of point to the Hochschild homology of Y. So Hochschild homology of point Well, what is it? It's just K. For instance, because point cross point is point, the diagonal lies module into the structure sheet, which is K, and comes between them. It's also K. So in particular, we get a point in this, if we think of this as a kind of vector space, we get a point in this vector space. So, call what one is, let's call it the trace of F. And so, I want to say what this is in terms of this identification of Hochschild homology. In terms of this identification of Hochschild homology, well, we can restrict a particular kind of a perfect complex as a vector model. So suppose F is a vector model. Then trace of F. So this lives in, again, this Hochschild homology space. Well, it's like an HH0 of light. I'm passing to homology, but what did we say HH0 was? It's sum over I, HI, x, omega I of x. And this is exactly, so, well, what you get, so this equals the term character of F. So, well, a term character is some combination of forms, but this exactly recovers the notion of the term character of a vector bond. So it's a sort of an abstract way of formulating what the term character is. So pushing this a little bit further gives a relatively simple proof of the Riemann-Roch theorem, which tells you about how these things behave under push forward. And what time did I start? How much time do I have?
You still have 5 minutes.
Okay, great. So that's one kind of nice thing about it. All right, so in the last 5 minutes, and maybe this will be a little bit of an advertisement for Demian's talks. I want to talk about one expected consequence of the field theory picture is, so remember, in the beginning I stated that if there's if we started with a compact Calabi-Yau, then we have a field theory associated with, which is the B model. And so the thing that associates to the circle is the Hochschild homology. And so in particular, that implies by rotating the circle, or by any diffeomorphisms. So if we take the orientation preserving ones, that's homotopic to just rotations. By rotating the circle, that's supposed to give an action of the circle on the Hochschild homology. So I want to sort of say something about what the geometric picture for that looks like. So in order to say this properly, one needs to pass to derived geometry rather than regular algebraic geometry. So in 5 seconds, so what derived algebraic geometry is about? Well, we have this functor. So this is another place where this functor of point of view becomes essential. Is that, well, regular algebraic geometry well, in some sense, or at least we saw that a variety was a special case of a functor from rings to sets. So derived algebraic geometry now is very simple to define. I just put the word derived in front of everything. So it studies functors from derived rings to derived sets. Of course, it doesn't tell you anything. But So let me tell you what these things are, really. So derived rings, well, these things, first of all, no longer form categories, but infinity categories. That's the thing. But derived rings, well, we're working in characteristic 0, so we can take, as our definition of derived rings, commutative differential graded algebras, which are connected. So in other words, which live in degrees less than or equal to 0. And derived sets is, well, it's a stupid name for something like topological spaces or simplicial sets. So that infinity category of topological spaces. So in particular, anything from this world has you can just interpret this as something in this world by a formal procedure. So any regular variety is an example of such a thing. But now there is something you can do. So this embeds here. So here's a construction from regular algebraic geometry, which is a little silly, but has a much more far-reaching version in the derived world. So what you can do is you can start with a variety, and you can look at its powers. So you can look at its square, you can look at its third power, and so on. And a little bit more abstractly, you can define a variety to the power of some finite set, or some arbitrary subset. And as a functor of points, so the x of variety, so x to the I, you define it as a functor of points on rings. This is by definition maps of I into whatever the value of x on that ring was. So it's an I tuple of points in x of r. So in the derived world, you notice that you can generalize this construction because now, because x of r is no longer a set, it's a topological space, you can take I to be any topological space. So if you take I to be any topological space and get a derived scheme, whatever that is. So in particular, I want to consider the example where I is the circle. So you might think, how in the world can I understand what this kind of abstract functor is? Well, the way you can understand it is the circle you can present as a colimit. So this is equal to, well, the circle is a push out of you sort of glue the two hemispheres along their intersection. And so one thing you notice about this, one formal consequence of this definition is that it takes push-outs to pull-backs. So this means that there's a fiber square of x to the S1 mapping to x to this guy, mapping to x to that guy, mapping to x to these guys. So this is just, so because this guy's constructible, this is just x. This is also just x. And this is, well, this is two copies of x. This is x squared. So from this we see that this mapping space from S1 into x is some kind of derived fiber product of the diagonal with itself. But now, the upshot of this is that, well, I told you about the base change formula before, and I said that when we pass to the derived world, the base change formula holds without any flatness assumptions. So from this we can see what. So we can understand the structure using base change. We can understand the structure sheet here in terms of these guys. Namely, if we take the structure sheaf here and pull it back, that pulls back to the structure sheaf. And maybe we want to understand, well, it's pushed forward back to x. That's the same thing as pushing forward to x squared and then pulling back. And so the option, and so what base change in this kind of consideration implies is that functions on x to the s1 is exactly the Harshal homology of x, because you take the structure sheaf of x, you push it forward along the diagonal map, and then you pull it back along the same map. And that was exactly the definition of Harshal homology. So already this implies, because this formula is completely natural in I, this formally implies that there's some kind of circle action. But explicitly, so implies S1 acts on Harshal homology. And the claim, which I'll end with, but don't really have time to explain, is that this action is given by the Durand differential.
Questions?
Yeah.
Can I ask about your board that you raised there?
Yes.
You were trying to convince me that if you have a projective manifold,
Yes.
say the final one, you wanted to derive the projective ring out of the kind of classical energies.
Yes.
And you started by saying that delta star of omega we know because this is our counter
Yeah.
in classical energies on x cross x.
Yes.
So I have a candidate, I don't know if we got it right, but I don't understand what is delta sub star.
Delta. What is delta lower star?
Right.
No, I didn't say what delta lower
Yeah,
star
right.
is.
So I wonder if delta lower star is the guy that corresponds to the cone, the identity of delta lower star of O. Because this we have access to.
Yes. Well, delta lower star of O, we don't necessarily know what that is.
Right.
If
So
we don't
you
know-
need to describe everything.
No,
that-
we're not describing omega. We're describing delta lower star omega.
No, this is what it is.
Intrinsically, without saying what delta lower star is, or without saying what omega is.
Exactly. I want to get either of these two guys.
But in general, you can't. So just knowing that, I guess I should mention. So I gave you some procedure. So in the case where the canonical bundle was ample, equivalently anti-ample, because you can reverse signs everywhere. How to reconstruct a variety from its derived category. So this would suggest that knowing the derived category is very close to knowing the variety. On the other hand, there are lots of examples of varieties which are completely different looking, but which have equivalent derived categories. And for instance, this equivalence doesn't respect either delta lower star or omega. So in general, you don't have much of a hope of recovering these
Delta lower
things.
star doesn't.
So that's not neither delta lower star itself nor omega is an invariant of the category. But the object delta lower star omega is.
And at some point you cheated me in the second board where you think I was convinced that you were using delta lower star, and that's why I started.
No, it wasn't. So we had an object of some category, so suppose we just start with a derived category of some variety. We don't know what the variety is, but the only thing that we know is that it's a projective variety with ample canonical line. Then we can produce what would have been delta lower star of omega in the category of functors from that category to itself. And then we can take shifts of this and powers of this, and we're allowed to take Hams between those. So what we were interested in is in Hams on x, not Hams on x squared. But as long as we shift down to the heart, then the h zeros will be the same. So that was the trick.
Other questions? Okay, if not, thank you again.